Okay, we're going to continue looking at Jupiter, and we're going to consider now its internal structure. One of the things that is very interesting about Jupiter is the fact that it radiates more energy than it receives from the sun. And that's a little bit startling. So the question that arises from that naturally is, where does that energy come from? How is Jupiter actually giving off more energy into space than it receives from the sun? So how is it possible that Jupiter's actually giving off more heat than it's receiving from the sun? It has to do with the way Jupiter formed. When Jupiter formed, basically all the things that made up Jupiter were attracted gravitationally and they condensed into the planet Jupiter. And that condensation was a source of heat. And Jupiter is actually still in the process of forming in the sense that it's still collapsing, albeit very, very slowly. And as this happens, it generates heat internally. Now, since Jupiter is so big and since it's got this internal source of heat, some people wonder, could Jupiter ever turn into a star? Because as we're going to learn later on, the sun is largely made up of the same kinds of things that Jupiter is made up of. So why is the sun a star and Jupiter just a planet? And that has to do with how big Jupiter is. Now, Jupiter is really huge compared to the planets, but it's tiny compared to the sun, which is, of course, way more massive than Jupiter. And in fact, in order for Jupiter to become even a faint star, it would need to be 80 times more massive. So there's no danger of Jupiter turning into a star, which would probably be bad for us if that were to happen, but it's simply not big enough to do that. But the fact that it does have this internal source of energy is an interesting thing. And I should note, we also talked about how the Earth has an internal source of energy that provides heat to the Earth as well as the energy that the Earth receives from the sun. But that was a completely different source of heating. That was from radioactive decay. The heating inside of Jupiter comes from this gravitational contraction, and that was what powers it even until today. Now, there's no direct information available about Jupiter's interior. We haven't sent probes deep into Jupiter to test our theories, but we do know that it's primarily made up of hydrogen and helium, and we know what percentages there are, and the behavior of these elements are very well understood. We know how it reacts at different temperatures and different pressures, and so we're able to deduce quite a lot about the structure of Jupiter, even though we haven't been able to send probes deep into it. And so we can see that as you go into Jupiter, the temperature and pressure go up significantly. So at a depth of about 100 kilometers from the outermost surface, the temperature is about 300 Kelvin. That's not that far away from the temperature of the Earth, but the pressure there would be about 10 times the pressure of the Earth. So that would be a little bit uncomfortable. As you go down 20,000 kilometers, the temperature has increased to 11,000 Kelvin, and the pressure is 3 times 10 to the 6 atmosphere. That's basically 3 million times the atmospheric pressure of the Earth. And as you keep descending, you get, the pressure of 40 million, temperature of 18,000 Kelvin. Remember, the temperature of the surface of the sun is only about 6,000 Kelvin. So the fact that the temperature inside of Jupiter is so hot is kind of startling. Now, just to be clear, the interior of the sun is much hotter than that. The surface of the sun, about 6,000 Kelvin. Now, as you get deeper into Jupiter, eventually the pressures are so great that the hydrogen and helium should actually become solid. And when you get to a depth of about 70,000 kilometers, we consider the core to be kind of rocky, and the temperature is incredibly high, 25,000 Kelvin, but the pressure is even higher. 6 times 10 to the 7, that's like 60 million atmospheres of pressure, which is just huge. Now, Jupiter is much too small to become a star. We've talked about that. It would need about 80 times as much mass. but its energy output was much larger in the past. Remember, we said that the heat that Jupiter is generating comes from the gravitational collapse. A lot of that heat is residual heat that was left over from when Jupiter first formed. And so its energy output should have been much higher in the past. And that would have mean it would have been much, much brighter. In fact, in the distant past, Jupiter could have been way brighter even than the moon, as seen from Earth. Now, it's kind of a staple of science fiction. There are many science fiction stories about what would happen if Jupiter were to be a star. And if Jupiter did have enough mass to become a star, that would have possibly made the planetary motions, especially for the inner planets, just too unstable. So that would have made stable planetary orbits kind of impossible. Um, One of the things, though, that we do note about Jupiter is that it is so big and so massive, and its gravity is so strong that it has this role of sweeping the solar system clear of debris. And so a lot of stuff that might come in from beyond Jupiter and might strike into the Earth is actually swept away because of Jupiter's strong gravitational influence. Without the presence of Jupiter, Earth could have been bombarded with so much stuff it might have made the formation of life here impossible, or at least greatly delayed. And certainly we would not likely be here at all. So we owe a debt of gratitude to Jupiter for being a kind of a gatekeeper and, in a way, protecting us from a lot of stuff that might come our way and do a lot of damage. Now, we've talked about some of the ways that Jupiter is similar to the Earth, and as many ways, obviously, that's very different. One of the things that Jupiter is similar to the Earth is that it has a magnetic field, a strong magnetic field like the Earth does. Now, the difference, though, here is that the magnetic field of Jupiter is incredibly large compared to that of the Earth's magnetic field. In fact, it's by far the largest magnetic field of any planetary body in the solar system. Its magnetosphere, which is related to the size of the magnetic field, it's 30 million kilometers across. In fact, I think this image depicting the size of the magnetic field of Jupiter is rather startling. You can see, so Jupiter, the red lines here in this figure are indicating the magnetic field around the planet Jupiter. And you can see that the solar wind coming from the sun has distorted the magnetic field, but it's so strong it extends out well beyond the orbit of Saturn. Now, in one of the earlier videos, I showed you sort of a scale of the distances involved and how far out Jupiter and Saturn are from the sun, and even how far Jupiter and Saturn are from each other. So the extent of Jupiter's magnetic field is just breathtaking. It's really amazing. And here you can see an image of the Pioneer space probe, which was slingshotted around Jupiter to pick up speed, and then went out beyond Saturn's orbit, and it was still detecting the magnetic field from Jupiter even this far out. So that was kind of an amazing thing to realize, just the extent of the size of Jupiter's magnetic field. Now, we've talked about the 4 Galilean moons of Jupiter, the 4 largest moons that were visible to Galileo in his early telescope, and those are Io, Europa, Ganymede, and Callisto. The Galilean moons are relatively large, and they have similarities to terrestrial planets, the so-called rocky planets like Earth and Venus, Mercury and Mars. So the Galilean moons have a very low eccentricity. You might remember things that orbit the sun, and as well as things that orbit the planets, they follow in elliptical orbits. That's just Kepler's first law. And the eccentricity has to do with how squashed out the ellipse is. If it's really flat, if it looks more like a line, that means it has a very high eccentricity. And if the eccentricity is very low, that means the ellipse is more like a circle. So these orbits are much more circular. Now, this is an interesting thing, I think. The largest of Jupiter's moons is actually larger than the planet Mercury. And so that's startling to me, that moon, if Jupiter were to go away, if it were to disappear and all the other moons, but that moon were to remain in Jupiter's orbit, it would be considered a planet. That's pretty straightforward. And we've actually talked in the past, you might remember, we talked about how Pluto was demoted from being a planet and what it is that makes something a planet. It has to be able to clear its orbit, it has to have enough gravity to make it spherical in shape, and so on. So some of these large moons that are around these gas giant planets, they could themselves be a planet, but because they're orbiting Jupiter or Saturn or whatever, they are not considered planets but are considered moons instead. Now, here is a beautiful photograph. I love this picture showing two of the moons against the backdrop of Jupiter. You can see the moon Io here and the moon Europa there, and the Great Red Spot provides a scale. Remember, we talked about how the Earth was smaller than the Great Red Spot. The Earth is, something like around this size. And that really gives you a comparison to how large these moons are. Next, we want to look at the moons of Jupiter. The four Galilean moons in particular. We have Io here, Ganymede, and Callisto. Ganymede is the largest. In fact, Ganymede is the largest moon in the solar system. And as I mentioned earlier, it's actually larger by volume than the planet Mercury, although it is less dense and has less mass than Mercury. Of these four moons, the most interesting by far is Europa. Now, you can look at Europa and you can see that it has an icy crust. That's a water ice crust. And it is believed, there is tremendously strong evidence to suggest that there is liquid water underneath the surface of Europa. In fact, there is more liquid water estimated to be in the moon of Europa than exists on all of the Earth's oceans combined. And this was a startling discovery that was only made relatively recently. Around the sun, there is a region called the habitable zone. If you're too close to the sun, it's too hot. You can't have liquid water on the surface of your planet, and the water will boil away. If you're too far away from the sun, it is the opposite. The water will freeze because it'll be too cold. But there's a region in space, a range of orbits that a planet can be in and have liquid water on its surface. Jupiter is so far out that no one ever imagined that there could be liquid water out in the outer parts of the solar system. But the discovery that probably there are these vast oceans of liquid water under Europa was startling. And we understand how that's possible from those same tidal forces. We talked about how tidal forces from Jupiter ripped the Levy-Shoemaker comet apart, but the same tidal forces are acting on the moons, and they cause the moons to stretch out like a ball of taffy, and they stretch and contract as the moon moves in its orbit around Jupiter. And that friction from that stretching, that contraction and stretching, creates internal heat. Just like if you rub your hands together, the friction from rubbing your hands together makes your hands warm. The friction from this stretching of Europa generates enough heat to keep the oceans liquid inside the planet. This is amazing because liquid water seems to be, at least on Earth, one of the main requirements for life. Where you have liquid water on Earth, you have life. And so that means that Europa is one of the most likely places for us to find life outside of Earth within our own solar system, life that has independently evolved and developed. And that can be anything from little bitty bacteria to more complex multicellular life. We simply don't know what's there, but that is one of the things that I think most astronomers, if you could say, okay, you're going to have unlimited money to fund one mission, what mission would you fund? I think an awful lot of astronomers would say, I want to go to Europa. I want to drill down through that icy crust into the ocean and send some probes down there and see if there's something swimming around in there. Because if we find life somewhere outside of Earth that's independently evolved, that is groundbreaking and it changes the story of us. So, why don't we do that? Well, because the crust of ice around Europa is kilometers thick, and it would be very difficult to drill through kilometers of thickness of ice on Earth. But doing it on the moon of another planet so far away, the engineering challenges are, beyond what we can currently do. But I think that someday, maybe even within our lifetimes, that might be a mission. A lot of people are very interested in seeing, is there life in the oceans of Europa? And that would be really, really exciting to find out if there are. Here are some more details about some of the other moons. So Io is the densest of the moons, and it's the most geologically active object in the solar system. It has many active volcanoes. It can change its surface features in a few weeks. Remember, when you have volcanoes, when you have earthquakes, when you have continental drift, these kinds of geological activities can reshape the surface of a planet. And so these volcanoes, these many, many active volcanoes, spewing stuff out onto the surface can actually change the structure of the surface. That's one of the reasons why Io lacks craters. It doesn't have craters because they just fill in too fast. Remember when we talked about Mars, and different parts of Mars have young surfaces compared to old surfaces. Well, Io has the youngest surface of any solar system object because of this immense volcanic activity. And again, those same tidal forces that we talked about with Europa generating the heat inside the moon to keep the water liquid, well, that's the same process that's keeping the geological activity on Io going. It provides enough internal heat to power these volcanic eruptions. Here we see an image, and you can see this sort of orange color, which is probably from sulfur compounds that are blown out onto the surface. And here is some more images, and we can actually see an image of a volcanic eruption. You can see this little box here. You can see that little burst there. That is that volcanic eruption. And that block is blown up in this little inset here. And here you can see another volcano, another segment that's blown up. You can see another volcano. So these volcanoes show just how active Io is. One of the interesting thing is that these volcanic eruptions, they eject charged particles into space, and these particles interact with Jupiter's magnetic field, its magnetosphere, and they form a torus, which is kind of a donut shape. The magnetic fields trap these particles in this donut shape. And so they're kind of similar in a way to the Van Allen radiation belts on Earth that we talked about previously. Now here is an image of Europa, which I talked about. That's the one that has the water underneath. You can see in this inset here that's blown up, this feature, you can see all these cracks in these structures. These look like, as you blow up and blow up, this looks like basically what we see in the Arctic, in Antarctica, among the different ices there. What's happening is that because of these tidal forces stretching and pulling on Europa, the surface actually cracks and water comes up from underneath and like freezes over. And that keeps the surface relatively smooth and flat compared to a lot of the other moons. Now, again, we have talked about Ganymede. It is the largest moon in the solar system. It's larger than both Pluto and Mercury, larger by volume, not necessarily by mass. Its history is similar to Earth's moon, but made of water ice instead of lunar rock. Now, one thing that is probably worth noting, Ganymede is much larger than the Earth's moon, but not compared to the size of its host planet. In other words, Ganymede is really, really large for a moon, but it's very, very tiny compared to the planet Jupiter. Jupiter is massively larger than Ganymede. However, when you consider the Earth's moon is huge compared, relatively speaking, compared to the size of the Earth. So, as a fraction of its host planet, our moon is the largest. But in terms of just raw volume, Ganymede is the largest physical moon in our solar system. Callisto is another one of the Galilean moons. It's similar in some ways to Ganymede, but there is no evidence of any kind of plate activity at all on the surface of Callisto. Now, one thing that a lot of people don't know is that Jupiter actually has a ring, just like Saturn's rings. In fact, all of the outer planet gas giants, Jupiter, Saturn, Uranus, Neptune, these planets all have rings, but Jupiter's ring is very thin and it's small. Saturn is, of course, the planet with the most prominent, the largest ring. You can even see the rings of Saturn through a relatively small telescope on Earth. But the rings of the other planets are much harder to see, they're much less evident, but they are there, so that's kind of cool. So we've covered a lot in these two presentations, so just a quick summary. One of the big things is that Jupiter is the largest planet in the solar system by far. We see that it rotates very rapidly. The cloud cover has three main layers. It forms zone and band structure. We talked about those different bands and the zonal flow of the atmosphere through those bands. We talked about Jupiter's most prominent feature, the Great Red Spot, and how it's a very stable storm. It's similar to like a hurricane on Earth in a lot of ways. We talked about its internal structure and how the pressure and density of the atmosphere increase as you go towards the center, and how the atmosphere becomes liquid and then metallic. It has a relatively small rocky core. I don't think I mentioned it previously, but that core is about 10 times the size of the Earth. So when we say small, that's relative to the rest of the size of the planet. It's still radiating energy from its original formation, and that's why it's actually giving off more energy into space than it receives from the sun. It has a total of 63 moons, but of course, four prominent large moons, the four Galilean moons. Io is interesting because of its active volcanoes, which arise from tidal forces. And Europa is, of course, interesting because it has this icy surface, which indicates that there may be huge oceans of liquid water underneath the surface. Ganymede and Callisto are similar to one another. They're mainly rock and ice, but Ganymede has the distinction of being the largest moon, not only of Jupiter, but in the solar system as well. So anyway, that is what I wanted to cover about Jupiter, and so I will see you next time when we talk about Saturn.